everybody today. So we are here. We're going to have Kristoffer Robin Stokke, PhD from the University of Oslo. He will explain how to create a minimalistic and probably the most basic computer using RISC-V and in a affordable FPGA. And we will be learning here how we can do that. A little bit more about Kristoffer Robin. So he has a PhD in informatics from the University of Oslo. He works today as a software senior engineer at RISC here in Oslo. He's very enthusiastic in low-level programming, assembly languages, operating systems, and has been working, I don't know, maybe 16 years already with C, C++.
Yeah.
And a little bit of Rust we will see in this talk.
Yeah.
And yeah, so this talk is hosted by NUUG, and after this we will go to Cafe Amsterdam for those who would like to come with us and join to continue the conversation. And yeah, remember to be a member of NUUG so we can have more talks like this. So then, please, Kristoffer.
Thank you very much for the kind introduction. And I guess I have to ask first, who here does VHDL? 1, 2, 3? Well, this will be pretty interesting. So, yeah. A little bit about this project and its history, which is now 1.5 years. It's a 1.5-year-old project. I, as Francisco said, come from the University of Oslo. I work at a peer. I have some colleagues here. I'm very happy with this. But on the side, I also do some teaching in the Informatics Institute at the University of Oslo. And I have assembler teaching, which is a great pleasure in 2026 to teach students the real world, so to say. So, and this is part of the really introductory course for, well, every year about 900 students in the first lessons that we try to teach computer architecture. And yeah, my part of this is the assembler part, and to teach the students as assembler, we use this simulator. Has anyone seen this?
Yes.
You've seen it?
Yes.
It's called a Little Man Computer, and we use this to teach the students how to do very, 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 very simple programming using assembler. And it's of course very simple. It has just 8 instructions, and it has an output field here, so it can write something to the user. It has an input field here, so it can take some input. And it has some memory, so that the little CPU that they're playing with, it can actually store and write some data. And it's a very, very nice simulator. But I've never been entirely happy with it. Because basically this is a decimal version of a machine. This is not a binary machine, this is a decimal one. And the reason it's decimal is for simplicity, because they are new students, right? But it's a kind of a strange way to teach computer science. And it's not a real machine. This is by far not a real machine. This is a simulated machine. In fact, it's 50 years old, this concept. That's called the Little Man Computer. And there's no way to bridge it like to the real world. There's no tool chain here. You can't program C for it, and nor Rust. So yeah, when you're trying to teach when I try to teach informatics to students, it becomes very difficult because you stand there with these 900 students and you talk about self-refresh and memory, virtual memory, paging, caches. You talk about the CPU execution cycle, right? Fetching instructions, decoding them, executing them, writing results back. You talk about bus registers like the memory and data address registers, program counters, stacks, and all this is very theoretical for them. Because this tool that they have, this simulated machine, is very simple. This is very difficult for them to understand. And but it's not right of me to blame this machine, because it's actually a great machine. It's a very, very cool machine. It's made by Peter Higginson. His photo is here. He's a retired computer engineer, and his name is actually on this plaque here, where well, he was one of the engineers who developed the original TCP protocol. And I've talked a lot with him during my working at the University of Oslo. And I actually went to meet him, and we talked about, you know, the troubles that we have in this course, and we actually came up with this. So this is something we made together. So we have an FPGA, which is actually running this decimal machine on it, which is kind of cool, right? So yeah. And this is kind of the, yeah. So how many here know what an FPGA is? Okay, that's very good. Mostly all of you, but some don't. So I just want to say something about it. So FPGA stands for Field-Programmable Gate Array. And what it is really like lots and lots of transistors, logic, that you can kind of configure to make various logical functions. You know, when we make computers, we make this integrated circuits. This is a Pentium 4, maybe recognize it. And inside it, there's like billions of transistors that do their job to make computation. But if you want to make a real machine, you can't really go and tape out these, because they are very, very costly. If you want to make this, it costs millions of dollars for just some tens of chips. So the closest thing you can come, if you have a wish to make your own computer in a circuit, the closest thing that you can come, in my opinion, is the FPGA, which is much cheaper, and you basically do kind of the same. And the FPGA that we use, the one I have with me here on the table, is a Max 10 FPGA. It's made by Intel, now Altera again. And this one I actually got from someone from Kongsberg called Ola Magnus Berge. He gave me this 2 years ago to play with. And yeah, then this is the FPGA we're using. And so me and Peter Higginson, we were sitting here and we were talking about, we made this LMC and then this FPGA, and then we did that, and then we celebrated with some beers. This is Håkon, this is my supervisor from my PhD studies. We have some beers and we talked about what we've done and the syllabus of this course, and he says to me, like, Robin, why not implement RISC-V? That's fun. Yeah, okay, so I guess my wife hates him for saying that. Yeah, and yeah, well, why not? For those who don't know, RISC-V is an open ISA, it's an open standard. It defines some instructions that you can implement to make a processor. But it doesn't define how to implement it, which is a good thing, because that means that you can take this specification, which says what instructions you need to be able to run, and you can decide yourself how to implement it. So it's very open. You can, if you're not satisfied with the performance of this RISC core, you can make your own. You can do it differently. You can do it better. Yeah, that's fine. I won't be sad. But the other thing is that it's a very, very simple. This is very simple stuff, because the RISC-V as a like standard collection is modular. So you have like at the very, very base of this standard, you have the RV32I, which is the RISC-V 32-bit base integer instruction set. And it's just like 35 instructions. That's the base, that's everything you need to build a computer that runs Linux or whatever. That's everything. And I say 35 instructions, but it's not really that complicated, because you can group them into basically 6 categories: jump instructions, load instructions, store, branching, integer, and logical, shift, XOR, and those kind of instructions. And then you, like the standard, allows you to build layers on this. So you have additional modules for multiplication, for example, atomics, floating point, instruction compression, and so on. So you can like build a pretty complex thing with this, but at the heart, it's this. This is what it all boils down to. This is a fully working operational processor that you can implement, and it's very simple, which is good if you want to teach how processors work. And what's really cool about it is that if you have one, you can just take like a C compiler or a Rust compiler, and you can build a program and you can have it run on this, which is pretty cool. So it actually also bridges the gap to reality. This is not a oversimplified training core. This is an actual simple CPU which is able to run whatever you want to run, really. And it's free, which is not the case for there are older processors out there, COF Spark 8, for example, which are also royalty free, but are much more complicated. And then you have, of course, cores that you need to pay for, like ARM, but this is completely free and open source. And you can also add your own stuff here. If you come in here and you have some great idea for an extension, you can make one. So it's very modular and designed to be open to the public. And I don't know if how many here have seen like a VHDL file? Not everyone. That's about half the room. I'm not going to show you code because that tends to make it pretty boring for people. So I would want to focus on what is the contribution here. And at the core of this contribution that I come to you with here, you have this RISC-V base integer CPU core. And to summarize it up, it's like a 4-stage pipeline processor. That means it has fetch, decode, execute, write back, and then it repeats this over and over and over. It has in-order execution, so it's very simple but slow. It stalls on memory, so if this core will try to do something on a bus, it will wait for a reply, so it will be very simple, but again, very slow. No branch speculation, so again, it will be slow, but very simple. And what's very cute, it runs on a 50 megahertz clock. So that's an increase from the last time that someone here heard me talk about this. Then it was 12 megahertz, now it's 50. So it's increased a bit. And the source code for this module is only 200 lines. So it's very small, very, very small. I don't know if you're used to, for those who are not used to VHDL modules, so of course VHDL is, when you make VHDL logic, you make entities, you make basically a component like this. And at the top level, you always say first what are the inputs, the input signals, and what are the output signals. And again, it's designed to be very simple. The core has an input clock, 50 megahertz clock. It has a reset to reset it when it starts. And then you have these blue boxes, inputs and outputs, and that's basically a very, very simple bus interface. So it can talk with other things. Right. And I don't want to go through lots of code, but so I'm thinking like if you're a student and you learn about like execution stages, for example, in the fetch execute cycle, then it will be relatively simple to open this code and look at what's actually happening in this core. So when it's executing instructions, it will execute instructions based on the opcode of the instruction it's working on. And I think this is a very, very nice way to see how the core works. And you can do this it's just one screen of code. So my question to you, now it's time for you to answer. Let's say, we have this RISC core, and you have the FPGA, and we put the RISC core in the FPGA. The question, is this enough? Yes? No?
No.
Why is it not enough?
On memory.
Memory, that's one thing, very good. It needs
some input and output to interface with.
Yes.
And a clock.
A clock, yeah, that's also very good. Yeah, that's very, very good. That's actually further than I planned. So that's yeah, that's very true. So let's this doesn't work because I guess we're doing hardware, so we'll do it the old way. So yeah, that's correct. You need some way to communicate the results, right? You need some output that you can say something. And this core also needs some way to get some input from the user. And you need some memory, preferably to store computations. And well, what about what should happen when this core starts? Anyone? So when you start this, what happens?
Loads from some address executes.
Yeah, it loads some boot code, right? There needs to be
you to switch all the switches and do that way.
Yeah, in the very old days. But it's still the same, just very small. And I also need, of course, some kind of bus to connect all this stuff together, output, input, RAM. Oh. So actually, it turns out that 1 year of coding VHDL in this project, I actually come to you with this is very simple now. The complexity is all this other stuff, which is also open source. So what do you need? So to do this, you need the FPGA board. This is pretty cheap. This is the FPGA board from Trends Electronics. It costs about 600 kroners. It was cheaper before, but... And of course, it will hold this RISC core inside the FPGA, which is here. And just for fun, in the start, me and Peter, we hooked up this LCD display. So as a means to communicate results. It costs about 150 NOK. And for memory, you have actually an SDRAM here on the development board. And here's the clue. So you can't really just use this. You need to build things so that you can use the RAM and use the LCD. So, first of all, to be able to write some characters to this LCD, you need a SPI LCD module. And that's also a module that I give you. And you need a RAM controller. This is also a module that is in the Git repo. This lets the CPU read and write data in the RAM, SDRAM. And then we need a read-only memory. It's pretty small, 4 kilobytes. And that's where the code that you put on this CPU is running from. And then you need some kind of traffic intersection, right? So that's when the core wants to access this stuff, it needs to go through some kind of traffic cross, right? You can look at it like this. So you have also a kind of we call it the crossbar that will direct accesses from the CPU, from the RISC core to the various modules. And this is an example of memory mapped I/O, which is also like a theoretical concept that students get. They read about it, but they like how can you understand this? Like, but at least some people might prefer to be able to look at this and see what is actually going on. Yeah. And the crossbar is like a the way it works is that when the RISC-V core wants to like access something, it will present an address to this crossbar. And depending on the first 4 bits in the address, the crossbar will route the request to various entities. So if the first 4 bits is 0, then the request will go to the SDRAM controller. And if the first 4 bits is a hexadecimal 8, it will go to the LCD frame buffer, and so on for the boot ROM. And that's the way to have the RISC-V core easily be able to access different memories, basically. So that's and this is not new. This is the Game Boy is also designed like this, but it has very, very small apertures. Of course, like a 8-bit processor, so not a lot of addresses to direct. Oh, and time for some demos. Yeah. So yeah, question.
Is the boot ROM in the FPGA or external?
It's in the FPGA. The boot ROM is in the FPGA. So it's a very simple module, and it uses the FPGA has RAMs in it that you use explicitly for this purpose. So yeah. Thank you for the question, and please raise your hand. We're happy to get questions. Yeah, so the first, this is like, yeah, the previous time I presented this project, it ended here, and the code that I'm about to show you running, it's actually handwritten assembler code, and I put some hearts around it because it's not human. It's not human to do this. It's a terrible effort. But I mean, I'm a kind of person who likes this. So yeah, I had fun with it, but I won't do it again. So but I think yeah. So I can just show you the demo. So so what this is I don't know if you can see it, but it's the demo is running. And what the assembler code is doing is that it's writing hello world. And then there's a counter from 0 to 9. And that's a counter in RAM. So that's how you test that the RAM was working. And then you have an animation beside there, which is just like a waving ASCII art with some Japanese happy eyes, I guess, or whatever you should call it. And yeah, this was like the first time this ran, which was pretty cool. My wife did not understand what I was doing, but and I must give some credit to her for being patient with me because this is taking a lot of time. So yeah, so I can't really, when I talk about assembler with students, they can't really. Resist trying to indoctrinate people a bit because it's like it's not human. But there are some examples of purely assembler written pieces of software that I always think deserves an honorable mention. This is who knows what this is? What game is this?
Roller Coaster Tycoon.
Yes, Roller Coaster Tycoon, and it was so smooth, running so smooth, no graphics card because it's just assembler. And of course the Pokemon games, like the greatest RPG games ever, that managed to squeeze a full RPG out of 1 megabyte of space. You have to admit that it's pretty impressive. Of course there are other things that are impressive written in C and C++ as well, but I always think it's cool to look back at it, and because I kind of respect the effort, because you have to be a bit stubborn to do this.
People didn't have smartphones back then.
Yeah.
That's why they read it.
And I presented this to Inventos. I don't know if we have Inventos people here, but probably not, I guess. But when I was there, I came with this, and I'm a software developer, C developer for over 10 years, and I hadn't written test benches for this. And they asked me, like, how did you debug your VHDL code without test benches? Like, how is that possible? And the truth is that this board has 8 LEDs and a button. So what I did is that I used the LEDs to tell me the state of the 32-bit processor. 32 bits is not enough, that 8 LEDs is not enough for 32 bits, so sometimes you have to be patient. And but I used the button as the clock, and then I stepped through the whole and it's and they were like screaming at me and like, why did you do this? And but now this code has test benches in UVVM but I found the reaction was very disturbing because it's I mean when it comes from software, it's like oh, just use the LEDs. Why not, right? And the thing is that once this was done, the project had lots of bugs, and then there was they had to fix, and which I fixed in the winter vacation, and it bothered me a bit because there's no way to actually give this board. Like, it didn't have a way to give the RISC-V core input. So that's a bit, I didn't like this, so I thought, okay, what's the simplest kind of input you can get? Well, that's probably UART. And I guess everyone might be familiar with UART. Or, so I don't need to explain a lot, but when you have an FPGA, it's very simple, right? So you can just hook up, you have lots of pins on FPGAs, right? So you can just hook up basically whatever you want. And UART is a very, 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 very easy, like a simple protocol, right? So you have just 2 wires, each communicating entity here has an RX line and a TX line, which goes to the other end, right? So I added this, and that's why I also have this UART to serial adapter, which costs a little bit, but not an insane amount. So for prototyping, this is fine. So that's the final. This is how it looks today, and I know there was a gentleman who mentioned the clock, and of course I didn't want to. I was a bit uncertain how deep we should go. So, but there is also a reset controller in here and a clock generator. I'm not showing it because they're very simple. But this is like the whole system as it is today. So the CPU can actually also use UART. So I guess what you need to test this, you need some gear. You need this Max 10,000 board from Trends, and you need this USB to UART dongle, and you probably need some prototyping cables. I would say around 800 to 1,000 NOK to build this board. But the rest of it is free, right? So you have the Intel FPGA, so you use Quartus, which is their tool chain to build FPGAs. And then you can use open source GNU and Rust compilers. And all the steps to set up this is in the project README in the Git repo. So if you want to test it. And I mentioned Rust, right? So what's up with that? Because I guess who thinks Rust is the new big thing? A lot of people do, right? I'm a pretty conservative, but I must admit sometimes I know that you have to be the future comes, right? So and I think actually it's a pretty nice language, to be honest. So this is a demo that I'm going to show you now. And this is the whole source code. So it's pretty simple. Its purpose is to print hello world or something to the UART controller. 2 things to note. This. When you're working at this level, there is no standard library. There is nothing. If you want to have a print function, you need to write it yourself. If you need a string tokenizer function, you need to write it yourself. You have nothing here. You're on your own. You have main, and then you have your head. And that's just how it is when you're running this kind of projects. But the nice thing is that everything is very visible. So you learn a lot when you're doing it. And then at some point, probably it might be nice to switch to something that has standard libraries, but yeah. And this is an example of, so what it's supposed to do is to print UART hello from Rust. And to do that, we use this memory mapped interface, right? So this is where it actually uses the bus to read and write registers on the UART controller to write characters. And I can show you then how it looks like. So if I already flashed the board, I'll show you how to flash it in a bit. But if I start this now, yeah. So that's Rust. Yeah, thank you. But I won't let you go yet. You have to watch C as well. Yeah, but yeah, that's Rust, and yeah, I think it's pretty cool that it's so simple to do it.
But I have a question.
Yes.
When you use Rust on this, isn't Rust very? Doesn't it take a lot of space?
Rust?
Yes.
No.
No?
No, it doesn't.
I was under the impression that it would.
I can show you after the presentation how much space it takes, because that's very easy to figure out.
But it's because there is no standard library.
There is no standard library, that's correct. Yeah. So that's why it's, yeah. But it's the same for C, so you strip away so much when you don't have the... Yeah. So, but I can show you the size after. So the repository structure is pretty simple. You have a software folder, which has bare metal software examples for C and Rust. And then you have a library and a projects directory, and those are the VHDL places. In the library, all the modules are, VHDL modules here are in the library. They are modules that you can just import to any project, and then you have the projects in the projects folder. So that's it. Really, that's how it's organized. And the intention here is that this should be so extremely simple that with like 1.5 years in IFE, you should be able to understand what is going on. So to run code here, you need, of course, the platform. But you can use the bare metal examples to write some amazing code. And then you run make. And then you open the FPGA project in Quartus, which is this project file. I'll show you in a bit. And then you build it. And then you load the FPGA image to the FPGA, and then you have it running. That's everything. And the components you need for this is, well, you need a linker script, because this is a memory mapped platform. So you need to tell the compiler, the linker, where it expects the code to be running from and where the RAM is, and so on. And you need a very small assembly file, which has one purpose: set the stack pointer. Also a very nice thing to see what is going on. And then you have the C code, which you can do whatever you want, as long as it compiles. So I thought I'd just show you that. And then we're almost, yeah. So I have this C demo that I'm going to show you now. And what it's going to do is that it's going to print some stuff on the LCD. It's going to yeah, print something on the LCD. I have some mix up here, but print something on the LCD, write hello world on the UART, and then it will perform a full memory check, because that's probably a good idea to check that all the bits are doing what they should. And then it will echo characters on the UART module, so it'd be like an echo function. So here's the, oops, I can try to make it a bit. This is the software hello world C directory. I'll type make. And what you're actually seeing here, coming out of this, that's the bytecode that is loaded to this boot ROM. So that's how I can show you this.
That's the hand assembly you were. That's the hand assembly you were talking about.
That would be the machine code. Yeah. And here it occupies about 363 times 4 bytes. Yeah, that's the C example. And what's happened here now is that it's actually put this code in a file that Quartus will use.
Using Markdown? It's using Markdown?
It's just moving it to somewhere Quartus will use it. So I can show you. But this is Quartus. And what I'll do is I'll open the project, which is, I have a shortcut here.
Is that free software?
That's free
Yeah.
software.
Free as in free,
Yeah.
or
Like
free
the
as
source
in
is available
Libre?
with no limitations to the usage?
Yeah. Don't shoot the messenger.
No, no. If you say yes to it's free software, I expect those things to be true.
I'm going to talk a bit about this at the end. Yeah. So for those who never used FPGAs before, this is not like software. So I'll press this button, and it'll start like compiling the design and compiling all the modules and fitting everything. This takes 1 minute for a very simple project. This is not... When you're doing FPGA, things are slow. They can take hours, actually, because you're trying to fit a design onto this fabric, and you have to reach your speeds and yeah. So I'll just stand here and talk a bit while this works, so we'll see how long it takes. But to answer your question, yeah, this is unfortunately, I'm a very fan of open source, but in the land of VHDL, unfortunately, vendors are proprietary. So you don't have the same openness, but there are things happening. There's a new company called, it's called, I don't have the, yeah, Cologne or something. I don't remember the name, but they have an Cologne chip, yeah. They have an open source toolchain. So there are things going on which is kind of advancing this into a place where we want to have it, so to say. But so far it's been, I guess, Intel, Altera, and Xilinx, who has been the big FPGA vendors, and their tools are just costly and proprietary, unfortunately. So, but this is changing, so let's see here.
Why are you using this over the others? Why are you using this software over the others?
At the time I started, this was the best option, to be honest. Yeah, the most open option.
Okay.
Simple to use, and so now it's almost done.
More expensive FPGA, it might go faster for the same job, or?
More expensive FPGA might be faster, yeah. There are speed grades, and yeah. And then you have more expensive FPGAs have more space for logic, and yeah. So this takes much longer today, I guess.
What do you do with the ELF files? Do you strip them?
Yeah.
Okay.
So when for example, the GNU toolchain makes an ELF file, which is correct, and then we have the script which just strips away all the debug and the unnecessary sections and dumps it into a binary format. Let's see here if I can. Now it's almost done.
You mentioned that the startup code was at initial address 4 or something. I think x86 starts at 0. Why did you do start at 0?
Where does x86 start? Where does it start, x86?
I think it starts at 000.
Does it? I don't know. I think the BIOS was proprietary.
Yeah, but the CPU just loads something from 000. Starting from there.
I don't know.
Yeah, I think so.
Yeah.
Why did you pick 4?
That's because I did. Because I did.
Just because he likes the number 4. He's a number 4 guy.
There's a convention in, I think, RISC-V about the typical initial address. I don't remember what it is, but there is some convention. It's not. You can't do whatever you want. It's not against the spec.
Yeah, you can do whatever you want. Yeah.
There's like one comment.
Normally this takes 1 minute, but today it's. I guess it's because it's the demo effect. No, it's. Yeah. So now it should start running. Yeah. Yes. Yeah. So this is now what it's doing is writing the whole RAM, except its own code and the stack, hopefully. We'll see.
And you can blame me.
And then it's reading. Now it's reading it again to check if anything is done. I actually had a bug with the self-refresh because originally I didn't have self-refresh on the STRAM controller. So after 2 minutes, some bits were off. But it's super fun to see this happening.
Is a program running now, testing the memory?
Yeah, and it passed. And now it should be in like UART echo, so it should be reading the UART and repeating. So yeah, and it works. So that's the C demo. And to conclude, yeah, I think it's I hope this can be interesting. I must admit that I don't expect. I mean, the main motivation is actually every year there's a group of 40 students of these 900 who are really keen on learning more, and I respect that not everyone wants to go this deep, but this is for those 40 that want to learn. And when things are this stuff is traditionally very hidden and very magical in many ways. I have a big BIOS manual at home from an old library in IFI 1. And it just doesn't tell you what things look like, but this at least should show you what it looks like. You can go into the code and you can check how things work. And yeah, so I hope it can be very inspiring. And of course, someone asked about the FPGA vendors, and they don't provide open source toolchains, I'm sorry. And also the simulation tools are typically totally proprietary and heavily licensed. So, but everything is changing. There are open source initiatives and there is progress, but it will take a long time before this opens up. And yeah, the question?
Yeah, comment on that. Now in USIS is the main open source toolchain for FPGAs.
Yeah.
And most of the stuff is kind of Verilog native, so that's another language. But there is a VHDL plugin now, which is mainline and quite common to use. And that allows you to target anything that USIS does, which is Lattice ICE40, Lattice ECP5, which is probably more the size that you have there. And Cologne Gate Mate.
Silence.
And Silence. So the only Altera is not there.
Yeah, well, let's hope
but
that...
that's an open toolchain.
Yeah.
VHDL is kind of like the second cousin right now, but there's a full toolchain that is actually seems, I think on the level of this, would work.
Yeah, that would be very nice to test. And I mean, I'm just one man, and I don't have a lot of time, to be honest. But my hope would be that maybe this could be interesting for people to continue developing. It would be nice to find more people who would take an interest, and maybe whatever suggestion you have, or I don't have like a big goal for this. I just will be happy if someone used it. So yeah, and it's also licensed. You can do whatever you want with it, I guess. So yeah, and this is really the conclusion, and I think I've been able to speak to you for 45 minutes. I'm very happy that you were so eager to listen. So thank you very much. Yeah.
Two questions.
Yeah.
One is, how much of the FPGA did this take, like all the implementation? Because there was the CPU and also the boot ROM.
Yeah, the gentleman asked how much space did this take on the FPGA, and that's actually I don't know, but we can check it very easily right now. So total logic elements 50% of the die, total pins 42%, and so I think about half of the chip.
Is it conceivable to have kind of 2 cores, kind of 2 CPUs running?
Yeah, it would. Yeah, it would definitely. Yeah. Multicore. That's a very good question. But there's also like the interesting aspect of it, because this is written to be simple, right? But it's also extremely inefficient, space and performance-wise. So as it would be interesting to see like how small you can make this core to be, and but of course there are open source cores that are much more high performance than this. So yeah.
I think there is one RV32 core that it's 200 cells
I heard. Yeah.
It's about the smallest. So you can have 40 of those.
Yeah. That would be extremely cool. Yeah.
That one is a bit serial.
Yeah. Yeah.
So for the writing the assembly code for the boot code, was that a choice, or was it possible to kind of transpile it from something a little bit higher level? Or?
What do you mean? The
Writing of the assembly code for the boot sequence.
Oh yeah, that was the first. Yeah, that was just because I had written a CPU and it wasn't working, and I hadn't even imagined beginning to test C. So that the first thing to do for me was, can I even do anything with this? Very, very simple. And it starts out by writing an A on the LCD, and that's 5 lines of assembler, and then you think, oh, this is cool. And suddenly you have like 50 lines of assembler, and not so cool. If you're interested, I can show you. It's since you're asking, you're very kind to ask. To be honest, I can show you.
What is the startup code doing?
Well, this is the assembler for. It's just hurts to watch because it's all of these are 32-bit indexes, and each one is a function to encode the various instructions, and these are numbers that I don't remember the meaning anymore. And it's
So you didn't actually write the assembly, you wrote the bytes.
Yeah.
Machine code.
I imagine the assembler. I imagine the assembler, but you know, when you're human and you start to write comments and what this thing is doing, it's just some people will call this masochistic.
Yes, it is.
Yeah. But that's I mean, you have to. I'm always impressed by, you know, people did this at some point, right? Yeah, they did, and you have to be a bit impressed by all the hard work that has been done. So, Any other questions?
People actually send people onto the moon with this.
Yeah. Yeah, that's a major feat. Yeah.
I wonder, for you professionally, seeing your work in the industry, yes. How did this help you in the industry?
I don't know if it helps me, to be honest. I don't know. I don't know, but the fact is that the RISC-V is really, I would say, it's a big game changer, right? And I know that a lot of industries are writing their own cores, and then you have all these open source cores, and this is by no means a competitor. This is just me and Peter having fun, I guess, and it's not by no means an attempt to compete with those cores, because but I think it will be maybe the future is very heterogeneous. Maybe you will have a lot of these specialized compute cores, and maybe FPGAs will be. I think several of my colleagues from previous jobs actually tell me that they use FPGAs because you can do very specialized things on them, and with very high performance, right? So, yeah.
Important stuff.
Yeah.
Regarding RISC-V,
yeah.
There was last year some initiatives to limit the access to RISC-V away from China.
Okay, yeah.
I don't know if you noticed.
I didn't notice, no.
Yeah. Do you think there is any possibility that RISC-V will be going away or be limited in access?
No. Can it now? Isn't that too late?
Not too late.
I guess it's. I don't think it. No, I don't think it will. To be honest, I don't see how that would be the case. But
There's one more over
yeah,
there.
yeah.
Please.
So you made this in VHDL instead of Verilog. Is that just like a personal preference, or are there some benefits for this kind of project to use VHDL?
That's a very good question. As I asked if it's VHDL versus Verilog and why I used VHDL. First reason, I'm a C developer, as I said initially, and VHDL looks a lot like C. So my initial approach was to code VHDL like C, which was horrible. But that's how we started, and I guess it was a bit lucky because what I hear from people at my workplace, we have a big FPGA group with 20 developers, FPGA developers, and what I hear anyway in the hallways is that the Americans use Verilog, and Europe uses VHDL. And I don't know if this is true, but I guess based on what they were saying, I would choose VHDL anyway. So yeah. So yeah.
Should we give the guy an applause?
Yeah.